Swayam Prabha. Digital India. Educated India.
So, okay, let's continue our discussion on Poisson process. So, before that, in the last class, we introduced what is a stochastic process, and then we introduced some properties like what is a counting process, and then what we meant by independent increments, and based on these properties, we defined a process called Poisson process. So, we are going to look at some of the properties of this Poisson process and try to prove them. As you will see that these properties you can directly derive from the definition, and they are also very appealing in the sense when you want to do kind of a counting, this property is what you desire. So, these are the properties we said that n is if a Poisson process, a random process is a Poisson process with rate lambda, that means n is a counting process, n has independent increments, and if you take any interval or any indices t and s, then the number of counts, so we said that this is nt minus ns has Poisson distribution with a rate which is lambda times the length of that interval t minus s. So, we are going to today see the following properties. So, we had said some random process to be a Poisson process. Now, we are saying that it has other equivalent characterization, that is you can say n is a Poisson process with lambda, that is equivalent to saying that the intercount times u1 u2. So, remember we have already defined what we mean by intercount times, that is between two count the time elapsed. So, that I am going to denote as this random variable u1 u2. Okay. So, they are random variables, right, for a process the time between two successive counts can be a random. So, that is why I am denoting them as u1 u2. They are these intercount times, they are mutually independent and also exponentially distributed with parameter lambda. So, all these u1 u2 they are identically distributed, further independent, and common distribution is exponential distribution. And this is same as saying if you are going to take any tau positive, then n tau, what is this n tau? This is the in the process the random variable indexed at time tau is Poisson with rate lambda t. So, if you are going to take any tau, this nt is Poisson distributed with nt, and if you are going to take any n, the conditional density of the first n count times. You remember earlier we have defined small t1, t2, t3, like t1 was the first count time, t2 was the second count time, like that, but this count itself can happen at random times. So, that is why I am now going to denote them as random variables with capital letters, and if you are going to look at the first n count times and that joint distribution, that joint distribution is given conditioned on the fact that this n tau has taken the value n, that is going to be given as n factorial divided by tau to the power n. So we are saying this is A is same as saying B, B is same as C, or A is saying same as C. All these are one implies the other. Okay. So okay, just now from this property we are going to look them, try to prove each one of them today. What it is saying is, if I have a Poisson process, okay, then the time of arrival between any two counts or the interval between any two counts is going to be exponentially distributed with rate lambda, and these intervals are going to be independent. The distribution of these intervals is going to be independent. And further, now if you focus on this, okay, so I have missed it. This is conditioned on the event n tau. Suppose let us say nt, if the Poisson process says that at the time tau n counts has happened, you are conditioned upon this. Now you want to see that what is the joint distribution of this. So first count happened at time index t1, second count happened at t2, and let us say the nth count happened at time tn. This distribution is going to be expressed like this, okay, and I should also. So notice that I am already saying till time small tau n counts has happened, and the joint distribution of this times is going to be this. So now if you focus on this part, forget numerator, now it is going to be like just now 1 upon t to the tau to the power n, right. So if I am going to look at a distribution of n random variables, and if it happens that their joint distribution is 1 upon tau to the power n, can you say something about what this joint distribution looks like? So just take n equals to 1, so I am saying 1 upon tau. So in the interval tau, I am saying something like the PDF is constant 1 upon tau, what that corresponds to? Uniform, right, something. Now I am saying the joint distribution of n random variable is kind of 1 upon tau to the power n. What does this imply in a way? What? Yeah, there are n uniformly distributed random variable, each with parameter tau, and they are independent, right. So they are getting multiplied 1 upon tau into 1 upon tau into. Further, I have to look at such kind of ordering these uniform random variables. Further, I need to condition that the outcome of the first random variable is smaller than the outcome of the second variable, and the outcome of the second random variable is smaller than the outcome of the third random variable. So I need to further condition on this. So if I further condition on this, I am going to get this factor 1 by n factorial in the denominator. So when the n factor goes in the numerator. So this n factor is coming due to the fact that I am looking for this t1 t2 be such that they are arranged in the increasing order. So in a way, there are two distributions that are related to my Poisson distribution. One is what? The exponential distribution, that is the inter arrival, the inter count times are exponentially distributed. And now if you look at directly the time of the count itself and the joint distribution, there seems to be some kind of uniform distribution that is coming into a picture here. So let us try to prove. Now what we are going to do to complete this proposition theorem, we need to show that each one of them implies each, right. So I have to show that A implies B, A also implies C, and if I take B, it should be the case that B implies A as well as B implies C, as well as if I take C, it should be the case that C implies A and C implies B. So instead of trying all this, what we will try to show is A implies B, and we will show that B implies C. So we will show that A implies B and then B implies C. So that should be sufficient, right, to show that each one. C implies B is already okay, oh sorry, I have to do this and then I will do this. Okay, let's say now let's try to show that A implies C. So let's assume that N is a Poisson process. So as soon as I assume N is a Poisson process, I have all these properties available to me, because that is the meaning of N is a Poisson process. So now let's take any N real numbers such that they are ordered like this, T1, T2 all the way up to Tn, where T2 is going to be larger than T1 and so on like this. So now think of them as, so this is T1, this is T2 all the way up to let us say Tn. So let us take an epsilon, and now what I am going to do is I am going to look at a small region. So I just take an epsilon and just go behind T1 and get T1 minus epsilon, and similarly around this I will go slightly epsilon behind and I get T2 minus epsilon, and this is like Tn minus epsilon. Okay, now what I want to do is I want to look at these intervals here. So this means I am open at this point, closed at this point, and similarly okay. Now let us try to find joint distribution of so what is this T1, T2, these are the count times and these are the random variables. So let us try to understand. Now let us try to find what is the probability that, so what is T1 here, capital T1? The time when the first count happens, right? So let us assume I am interested in this, Ti belongs to okay. So what is this telling? I am interested in, when I take T1, I am asking the question, the probability that the first count happen in this interval T1. So T1, T2, they are some given numbers to me. Now Ti is a random variable, right? Now I am basically asking the question, okay, this Tith, that means the ith count happening in this interval. Okay, and now I am looking at a joint distribution and I want this to happen, this condition for all I 1 to n. Now now I want to express this in such a way that I can go and apply my independent increment properties. So let's say I want to apply this. How can I express this probability to exploit my independent increment property? So one thing I can now do is, what I am basically asking is, the first count should be happening here, right? That is T1, capital T1 is T1 minus epsilon and T1. If that is the case, then there should be no count happened before that, right? And the first count should have happened here. And then if I want T2 to be again in this interval, no count should have happened in this interval, and the next count should have happened in this interval. Then my T2 is going to fall in this interval, right? So then this is same as asking, is this correct? I can express this joint distributions like this, that is nothing happens here and the first count happened here and the second count only happened here, that means nothing, I do not want any count to happen here, and like that, and the last count happens only in this region. So you see that now I have expressed this quantity in terms of the increments. Okay. So now I want to expand this. If n is a Poisson process, are all of these events are independent or not? Because I am looking at the different intervals, right? And I know that for Poisson process they are all independent. So and now I am going to further exploit the property that, so now if I am going to look at, no, first consider the case, so I can write them as probability. Okay, just let me write it for in terms of the probability first. Probability this is for the first one, and the last one is going to be right. I have simply applied my probabilities on each one of these. Yes, right. Now this is coming from what, like as I said, this is coming from independent increment properties. Now further, what is the third property of the Poisson process? It is going to be Poisson, right, like if you are going to. So I could as well write this guy as like n minus 0 here at 1, and I could just take n0 as 0 itself. Now what is this probability is going to be? Sorry, this is 0. What is this? What is the length of this interval? T1 minus epsilon, and I am asking, so this is going to be Poisson process with what rate? Lambda into T1 minus epsilon, right? Now what is the probability that a Poisson process with rate lambda T1 minus epsilon takes the value 0? E to the power, here the length of the interval is simply T1 minus epsilon, right? Now what is the probability that it takes value 1? The length of the interval here is, it is simply epsilon. So here it is a Poisson process with rate what? Lambda epsilon, right? And what is this value is going to be? Lambda into lambda epsilon, and there is a one factor in the denominator which we can skip, right? So like this you can keep writing for all of them, and just let's write what is this looks like. E to the power lambda, this is going to be what? Tn minus 1 minus Tn plus epsilon, and the final one is going to look like lambda Tn minus epsilon. Here this is going to look like epsilon e to the power lambda epsilon again. So now if I am going to simplify all these things, there are how many lambda epsilons getting multiplied here? There are going to be n1 of them, and if you are going to simplify all of them, you see that some subtraction is going to happen because T1 is happening, it will also come as minus T1 later, and if you are going to simplify that, what it will end up is simply e to the power minus lambda Tn. Okay. So whatever this probability I was looking at, this joint distribution, it is now lambda epsilon. So this I am going to simply write as lambda n epsilon n into it or lambda Tn. And now let us say I now want to take this probability that Ti belongs to Ti minus epsilon, comma, divided by, if I want to do this epsilon n, this is going to be equals to lambda n to the power e to the power lambda Tn, and that is what I have shown. So now if you are going to see what I am doing here, for a given T1, T2, Tn, I am looking at for each of these Ti around an interval of epsilon length, and now everywhere these lengths are of epsilon. So what I am basically looking at for a given this T1, T2, I am looking at the mass of these random variables in a ball which is of what volume? So for example, let us take a simple case. I have now taken, let us say this is my T1 and this is my T2. On T1 I have looked at a interval of epsilon, and also on T2 I have also looked at an volume of epsilon. So what is this region is going to be? This region is going to be, I was basically looking for my T1, T2 to be in this region here, right, where T1 is of length epsilon and T2 is also of length epsilon. So what is the area here? Epsilon square, right. So if you are going to extend it to n dimension, what is this volume is going to be? X epsilon to the power n. So now this is what I want to do. I was basically looking at these joint distributions to lie in some volume which has which is epsilon square. Now that probability I am dividing it by epsilon n square, and now what I got is lambda to the power n e to the power lambda n. Now this epsilon I have chosen is arbitrary, right. I could as well let this epsilon go to infinity here. Even if I take epsilon arbitrarily small, this ratio is kind of independent of lambda n, right, this value is going to remain the same. So if I take this ratio and let epsilon go in, let epsilon tend to 0, what this ratio will converge? What is this ratio according to our definition? So you remember the way how we defined our PDF and we connected it to the probability. So what we had said? We had said that f of x at a point x can be thought as limit as, this is in all one dimensional case, as epsilon tends to 0, probability that x is, let us say, in this interval x minus epsilon, x plus epsilon divided by epsilon. Did we say this when we are trying to argue the relation between a problem, when we try to give an interpretation of what we mean by a PDF of a point at a given point? So we are dealing here with what, like we are dealing here with continuous random variables, right. This t's here are the continuous random variables. T is the count time, right, they can take any number on the real value. So here we are dealing with a continuous random variables. So when we try to give an interpretation for our PDF, we had said that PDF of a random variable x at a point x can be thought of its probability in the neighborhood of x, where that neighborhood is defined in terms of epsilon, and we can make that neighborhood small by letting epsilon go to 0, and when we take this ratio, that is nothing but the PDF. Yeah. TI? Yeah, these are finite, but each one of them is a continuous random variable. I am talking about individual one, right. So each one of them itself is it can take any real number. So if you have this probability and if you just let epsilon go to 0 in this fashion, that is nothing but the CDF. Now we can apply the same definition here, right, but here instead of a real line we are in a n dimensional space. That is what, instead of just epsilon, we are looking at epsilon to the power n, which corresponds to area, which is the volume in the n dimensional space. So due to this, we could now write f of T1, f of T1, T2 all the way up to Tn, the joint distribution of this to be what? Lambda to the power n e to the power lambda Tn, provided what is this? This T1 is greater than T2 and all the way up to Tn, and now we have 0 otherwise. Is this correct? Are you convinced? And what is this? This is the joint distribution of this random variables. So this is what we just derived by using the properties of my Poisson process. So it is clear that we use our second property here of the Poisson process, that independent increments, and then we use the properties of Poisson distribution, the third property here. So did we use anywhere the property, the first property which said that the Poisson process is a counting process? Anyway we use it, right, because one of the properties of the counting process, n of 0 is 0, right? I mean we use part of that, like counting process is much more, but we partly used some part of the definition of it being a counting process here. Okay, now we have, but this is not what we are interested in, right? Fine, we have come up with the joint distribution of my count times, but what I am interested to show property B is the distribution of my intercount times. Okay, now how to derive a joint distribution of the intercount times using the joint distribution of this count times themselves. So if you want to derive, what property you can exploit now? Is there a way you can think of? So from this I basically want to now go and write what is the distribution, the joint distribution of these random variables. So if there is a relation between these u's and these t's, I should be able to apply my transformation of random variables properties and should be able to derive this, right? We have already studied that, but now the question is, what is the relation between these u's and t's? So we already know that, right, like ui ti minus ti minus 1. So we know this relation. Now how can we write this joint distribution in terms of f of x, f of t's here? What is the property? What is that we know about this? So we know that, right, when we have to write this distribution, we need to compute the Jacobian. So what is the thing? So we have this. So let me write it more explicit. We have u1 equals to t1, u2 equals to t2 minus t1, and like that. And also we know the other way around, right? So t1 anyway equals to u1, and what is t2? u1 plus u2, and t3 is u3 u2 u1. All this we know, right? So how to write this then? So we already know that this is nothing but u1 to un of un u2 to un is equals to f of t1 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 way up to tn. What was this? And what we had here? A Jacobian matrix, right? Determinant of a Jacobian matrix. And what was that? So can somebody quickly compute what is the Jacobian matrix here? It's going to be 1. Why is that? You are just going to get a, so whatever, you can just compute that, and finally whatever we want here will have a unit determinant. So now how to express this? I have this t1, but t1 is u1 and tn is sum of all the random variable, but this distribution only depends, sorry, it should be tn here, on tn here. So what is tn in terms of u's? Tn is nothing but sum of ui's, right? So because of that you could write that as lambda n e to the power minus lambda and this is for any u, and this is going to be 0 otherwise. Now from this did we conclude what we wanted to say here? I am looking at the joint distribution of u1 u2 all the way up to un. Now what I have done is finally able to show that give me any u, this can be expressed as lambda to the power n e to the power lambda u1 plus u2 up to un. So what is this basically? This is nothing but the product like lambda e to the power lambda u1 into lambda times e to the power minus lambda u2, like that, right? I can split it as the product of n such terms, and what is each term there? What is each term there? It's an exponential random variable with parameter lambda. So that is what exactly the claim. And why I am saying independent? Because this joint distribution I am able to express is a product of n distributions, right, and each one of them now corresponding to exponential random variable with lambda. So that is why this claim holds. Okay. So as you see, I mean if you have a Poisson process, that means nothing but if you just look into the intercount times, the collection of intercount times, they are nothing but they are Poisson distributed with the same rate lambda. So if I say I Poisson process with rate lambda, or I say I have a bunch of random variables which are a random process where each random variables are independent and everybody has a Poisson distributed with rate lambda, that means I am basically referring to the same Poisson process with rate lambda.